Hello everyone, let's go over the laws of thermodynamics. The first law of thermodynamics says that energy cannot be created or destroyed, but it can be transformed or transferred. This comes from the law of conservation of energy. In practice, the first law sets the equation for the system you're looking at, describing the relation between variables like internal energy, heat, and work. The second law of thermodynamics is entropy. It states that the entropy of a system and its surroundings will always increase, and as such, the entropy of the universe is always increasing. A more simplified version of this is that heat will flow from a hot region to a cold region. The two common formulations of the second law is Kelvin's and Clausius's approach. Kelvin's formulation of the second law basically says that in practice, a heat engine cannot be 100% efficient. So imagine you have a heat bath, labeled TH on this diagram, which transfers heat, labeled QH on this diagram, to a heat engine which uses the heat to create work. Kelvin's formulation of the second law says that the heat engine will also produce heat, given by QC on the diagram, and it will need to dump that heat into a heat bath, labeled TC. And the efficiency of an engine can be calculated by taking the work outputted from the engine and dividing it by the heat that was input into the engine. And Clausius' theorem for the second law of thermodynamics says that no perfect refrigerator exists. What this means is that a refrigerator, which operates like a reverse heat engine, can't take heat from a cold body, thus making it colder, and give that heat to a hot body, thus making it hotter, without any external work being input into the system, that is. So simply put, a refrigerator will always need work added into the system to operate. Instead of calculating efficiency like in a heat engine, refrigerators calculate performance, given by lowercase w, is equal to the heat from the cold bath divided by the work done, or the heat from the cold bath divided by the heat from the hot bath minus the cold bath. Moving on, the third law of thermodynamics says that the entropy of a system will approach a constant value of about zero as the temperature in the system approaches absolute zero. As a consequence of the third law of thermodynamics, it's impossible for absolute zero to actually be reached for any system. For proof, let's look at a plot of entropy versus temperature. Suppose we can reduce the temperature of some substance by changing the parameter x from x2 to x1. So we can lower the temperature in the system in discrete steps, the greater change in temperature happening when there's a greater difference in entropy. But as we further reduce the temperature, the entropy difference gets smaller and smaller. And according to the third law, near absolute zero, the entropy is constant, meaning that we would need an infinite amount of steps to reach absolute zero. Thus, it is actually impossible to cool a system to absolute zero. And lastly, the zeroth law of thermodynamics defines thermal equilibrium. It says that if two systems are separately in thermal equilibrium with a third system, then the first two systems are in thermal equilibrium with each other. The main outcome of this law is that it provides a definition for temperature without needing to reference entropy, like how the second law does.